A Brief History of Time by Stephen Hawking, read by Mr. Narrator. Maxwell's theory predicted that radio or light waves should travel at certain fixed speeds, but Newton's theory had got rid of the idea of absolute rest. So if light was supposed to travel at fixed speeds, one would have to say that fixed speed was to be measured relative to. It was therefore suggested that there was a substance called ether that was present everywhere, even in the empty space. Light waves should travel through ether as sound waves travel through air, and the speed should therefore be relative to ether. Different observers moving relative to ether would see light coming towards them at different speeds, but light's speed relative to ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit round the Sun, the speed of light measured in the direction of the Earth's motion through the ether when we are moving towards the source of light should be higher than the speed of light at right angles to that motion when we are not moving towards the source. In 1887, Albert Michelson, who later became first American to receive Nobel Prize for Physics, and Edward Morley carried out a very careful experiment. The Case School of Applied Science is Cleveland. They compared the speed of light in directions of the Earth's motion that at right angles to the Earth's motion. To their great surprise, they found they were exactly the same. Between 1887 and 1905, there were several attempts, most probably the Dutch physicist Hendrik Lorentz, who explained the result of the Michelson-Morley experiment in terms of objects contracting and clocks slowing down when they moved through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in the Swiss patent office, Albert Einstein, pointed out that the whole idea of an ether was unnecessary, providing one was willing to abandon the idea of absolute time. A similar point was made a few weeks later by leading French mathematician Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regarded this problem as mathematical. Einstein is usually giving the credit for the new theory, but Poincaré, remembered by having his name attached to the important part of it. The fundamental postulate of the theory of relativity, as it was called, was that the laws of science should be the same for all freely moving observers, no matter what their speeds. This was true for Newton's law of motion, but now the idea was extended to include Maxwell's theory that the speed of light, all observers should measure the same speed of light, no matter how fast they are moving. This simple idea has some remarkable consequences. Perhaps the best known are the equivalence of mass and energy, summed up in Einstein's famous equation E equals to mc square, where E is energy, m is mass, and c is the speed of light, and the law that nothing may travel faster than the speed of light, because the equivalence of energy and mass, the energy which an object has due to its motion will add to its mass. In other words, it will make it harder to increase speed. This effect is only really significant for objects moving at speeds close to speed of light. For example, at 10% of the speed of light, an object's mass is only 0.5% more than normal, while at 90% of the speed of light, it would be more than twice as its normal mass. As an object approaches the speed of light, its mass rises ever more quickly, so it makes more and more energy to speed it up further. It can in fact never reach the speed of light because by then its mass would have become infinite, and by the equivalence of mass, the energy it would have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speed slower than the speed of light. Only light or other waves that have no intrinsic mass can move at speed of light. An equally remarkable consequence of relativity is the way it has revolutionized our idea of space and time. In Newton's theory, if a pulse of light is sent from one place to another, different observers would agree on the time that the journey took, since time is absolute, but will not always agree on how far the light traveled, since space is not absolute. Since the speed of light is just the distance it has traveled divided by the time it has taken, different observers would measure different speed of light. In relativity, on the other hand, all observers must agree that how fast light travels. They still, however, do not agree on the distance the light has traveled, so they must therefore now also disagree over time it has taken. The time taken is the distance the light has traveled, which the observers do not agree on, divided by the light speed, which they do agree on. In other words, the theory of relativity put an end to the idea of absolute time. It appeared that each observer must have his own measure of time, as recorded by a clock carried with him, and that identical clocks carried by different observers would not necessarily agree. Each observer could use radar to say where and when an event took place by sending out a pulse of light or radio waves. Part of the impulse is reflected back at the event, and the observer measures the time at which he receives the echo. The time of the event is then said to be the time halfway between when the pulse was sent and the time when the reflection was received back. The distance of the event is half the time taken for this round trip multiplied by the speed of light. An event in this sense is something that takes place at a single point in space at a specified point of time. This idea is shown here, which is an example of space-time diagram. Using this procedure, observers who are moving relative to each other will assign different times and positions to the same event. No particular observer's measurements are any more correct than any other observer, but all the measurements are related. Any observer can work out precisely what time and position any other observer will assign to an event, provided he knows the other observer's relative velocity. Nowadays, we use just the method to measure distance precisely because we can measure time more accurately than length. In effect, the meter is defined to be the distance traveled by light in 0.00000003335640952 seconds, as measured by the Celsius clock. The reason for that particular number is that it corresponds to the historical definition of meter in terms of 2 marks on a particular platinum bar kept in Paris. Equally, we can use more convenient new unit of length called light second. This is simply defined as the distance of light in 1 second. The theory of relativity, we now define distance in terms of speed and time and the speed of light, so it follows automatically that every observer will measure light to have the same speed. By definition, 1 meter per 0.00000003335640952 seconds. There is no need to introduce the idea of an ether whose presence anyway cannot be detected, as the Michelson-Morley experiment showed. The theory of relativity does, however, force us to change fundamentally our ideas of time and space. We must accept that time is not completely separate from an independent space, but it's combined with it to form an object called space-time. In a matter of experience, that one can describe the position of a point in space by 3 numbers or coordinates. For instance, one can say that a point in a room is 7 feet from one wall, 3 feet from another, and 5 feet from the floor. Or one could specify that the point was at the central latitude and longitude and a certain height above sea level. One is free to use any 3 sustainable and suitable coordinates, although they have only a limited range of validity. One would not specify the positions of moon in terms of mile north and miles west of Piccadilly Circus and feet above sea level. Instead, one might describe it in terms of distance from sun, distance from the plane of the orbits of the planets, and the angle between the lines of joining to the moon to the sun and the line joining the sun to a nearby star such as Alpha Centauri. Even these coordinates would not be of much use in describing the positions of the sun in our galaxy or the positions of our galaxy in the local group of galaxies. In fact, one may describe the whole universe in terms of collections of overlapping patches. In each patch, one can use a different set of coordinates to specify the position of a point. Here is the photo of the radar.